Okay, so welcome to the second lecture on elliptic curves today. We're going to be talking about models for elliptic curves, and we've talked a little bit about models in the magma session, but I'm going to start now going through elliptic curves just a little bit slower than in that whirlwind of a first talk. So what I'm doing is actually, I'm following mostly my own book. This book is an introduction to number theory, elementary number theory sort of from the beginning, but it also has chapters 15 and chapter 16 are on cubic curves. So it has a lot of the elements about how to do changes of variables, and then this sort of like introduction to elliptic curves. This book is free. There's a free copy available in my website that you can get. Okay, so what's my goal for today is to get you in the 5%, in this 5%. So I don't know if you've seen this meme, but this is actually a De Fontaine equation that is pretty hard to solve. I think 95% they were being very generous. I don't think it's 5% of the population that can solve this equation. But what is true is that this is the simplest such equation of apple, bananas, and pineapple. This is going to be a fruit that starts with C. I don't know why they chose pineapples. In any case, how are we going to solve this? Is this an elliptic curve to begin with? So I'm going to use this sort of as the running joke, I guess, or running example until we get to the point that we find this solution to that elliptic curve. So how do we find this? First of all, it doesn't have to be like this. It's going to be like that. Okay, so first of all, what we're going to do is write an actual equation that doesn't have fruits, mostly because I can't draw fruits very quickly. Otherwise, I would have kept fruits all along. But in any case, this is the equation that we are trying to solve. Is that a De Fontaine equation? Yes, no, not as is. So if you clear denominators, then you get to this equation, and this is an equation, a polynomial equation in 3 variables with integer coefficients. So that is a De Fontaine equation, and that's what I'm trying to solve is this De Fontaine equation. Notice that the problem, very important, very, very important, the problem asked for can you find the positive whole values for the apples, bananas, and pineapples? Positive. Okay. If it's not positive, then we'll see that there are easier solutions. But to begin with, is this an elliptic curve? And if it is, then how are we going to find points on that elliptic curve? So an elliptic curve, before I told you, is a smooth cubic curve. An elliptic curve is, in fact, over a field f, is any smooth projected curve of genus 1. So we can actually drop the cubic assumption. Just any curve that is of genus 1 in projective space, in the projective plane. So what that means is that as a complex variety, so let me actually write it down here, that when I look at it over the complex numbers, it is going to look like a donut. It's going to have that surface, is going to have a one hole. There's, of course, a much more rigorous definition of what genus is, especially because if the field is other field that is not like Q or the reals or something, then like how do we define field? How do we define genus in our arbitrary fields? Yes, there's a question.
Could you give me a rough definition
of variety? So a variety is, so a curve is a variety, is a dimension 1 variety. Variety is an object that is defined by polynomial equations. So by one or several polynomial equations, the 0 set of a number of polynomial equations, for me that is a variety. The word variety is usually reserved for, there's some certain qualities to the, what I said, a set of points that satisfy some algebraic equations, that's some algebraic set. To be a variety, the affine ring of that object has to have some properties, but I'm not going to go there. Just think of things that are defined by polynomial equations. That's a variety. And if it is a dimension 1, so I can also just go into algebraic geometry and define dimension. But if it's a dimension 1 variety, then that's a curve. Usually curve, we'd say is smooth, but to be clear, it has to be a smooth dimension 1 variety. So something algebraic, dimension 1, smooth. Genus 1, again, if I take that over Q, if I upgrade to the complex numbers, it will be some surface like that. It has to have just one hole, that is genus 1. And as we discussed in the first lecture, I'm going to assume that I have at least one point to begin with, so I can start doing some number theory on it. And these are, any other questions? Yeah. Where does what come in?
These equations are all cubic, right?
So not in here, not in here. So in this definition now, in the previous lecture, I did say we were going sort of by degree of the Diophantine equation, and we stopped at cubic equations, and those are elliptic curves. But not every elliptic curve has to originally be given by a cubic equation. I'm going to get to that in a moment, that if I have a genus 1 curve, if I have an elliptic curve, there will be a transformation that gives me a cubic equation. So it can be given by a cubic. So but there's some elliptic curves that are given by quartic equations. But there is some change of variables that actually gets rid of that 4th degree element, and it brings it down to a cubic equation. Okay? Smooth means that there is no singularities. So if you take your defining equation, for example, just as an example here, what is this? This is a circle, so it's just a graph like that, so it's smooth. Otherwise, if I have, I have right here an example of something that is smooth. This one is singular because at 0, 0, there is what we call a cusp. And what happens is that at any point here, I can define a tangent line, and there's a well-defined tangent line. You take the derivatives to define the tangent line, and there's a very well-defined tangent line. But at that point, at 0, 0, there is no well-defined tangent line. The derivatives vanish. Both the partials with respect to x and with respect to y vanish at 0, 0, and I can't pick a tangent line correctly. Okay. Yep, exactly. So if you're working over an arbitrary field, for example, like what does this mean over a finite field? What it means is that I'm going to generalize that notion of partial derivatives to that function field. So I'm going to take formal derivatives of the polynomials. Or there is another definition. If you start learning about ellipticals, for example, from Silverman's book, you learn about algebraic geometry and the affine rings. And there is a definition of singularity in terms of the ring of functions that is much more general. And you can prove that are equivalent, your partial derivatives from calculus and this definition using ring theoretic definition, they actually coincide when the partial derivatives exist. Yeah. So, okay, so we have affine curves, and there are projective curves. This is the same, this is the affine curve. This is a projectivization of that curve. What you should think is that projectively, we have extended our affine curve into the projective plane, and this is now a chart. This is a piece of that projective curve. And there are several charts depending on, I can make a chart so I can look at the points at infinity, so some sort of affine plane that does have, that point is on the affine plane. So usually what happens is that there is, the projective plane, you can think of it as the Riemann sphere, something like this, and then usually we look at circles. The circle is here. And okay. And so that's usually what happens. But if you're looking, for example, at a hyperbola, in a hyperbola, when you look at it, a hyperbola in the affine plane will look something like this. But what happens is that in the Riemann sphere actually sort of like wraps around, and it is sort of like an ellipse in disguise. It's just that the way they connect is sort of in the infinity chart of the sphere. Okay, so that is the distinction between the projective and affine, but we are looking at our curves always in projective space and making sure that the smoothness happens in projective. They have to be smooth instead of singular. They have to be genus 1. So this is a curve of genus 1, while this is a curve of genus 0. Again, if you look at the complex version of this, does have a hole like this. The complex version of this is just the Riemann sphere, so it doesn't have any holes, so the genus is 0. Now, curves can have no points over the rational numbers, right? There's no real points, so they cannot be rational points, so there's no points at all. And there can be points. So to have an elliptic curve, we need, it's non-singular. It has to be genus 1, and it has to have some points over Q. Okay.
Can there be a curve that is genus 1, but it's not a cubic?
What's that?
Can there be a curve that is cubic, but not cubic, but genus 1?
Yeah, so it can be a priori, a curve can be something like y squared equals, I think, x to the 4th plus 1. It's a curve that has genus 1. It looks like it's given by a quartic, but there is a transformation that brings it to a cubic equation. There is, I think in the book, there is some example like that. There's an exercise that transforms certain types of quartics to cubics. Yep. So some good news is that a projective smooth cubic curve with at least one point is an elliptic curve. So the cubic curves that are smooth and have one point, those are elliptic curves. Okay, so there's a big chunk of elliptic curves that come like that, and then there's other, as I said, some other curves that can be change variables to a cubic, and then they are also elliptic curves. So let's see our example, the Fruits-Diophantine equation. This is, in fact, projective. It has 3 variables, but it's homogeneous of degree 3 everywhere. So this is projective, and this is a curve. I can make a chart, an affine chart, by just changing what happened from here to here is that I'm changing little x is x divided by z, and little y is y divided by z. And then I get an affine chart. Keith?
This addresses the point asked earlier about why points with z equals 0 are considered at infinity.
Oh, right. Right, the fact that with this change of variables, if z equals 0, it sort of explodes. The coordinates are sort of like at infinity. The coordinates become infinite. Okay, so this is an affine model for this projective curve. So I'm trying to find rational points on this one. You can check that it is a non-singular cubic. We did that in magma earlier with another type of curve. So you can put this one on magma and check that it's non-singular. And it has a rational point. Can you find a rational point here? Oh, so you can. That's a good question. So you could say a Q point, and that means that it's a point defined over Q. But many times we will say F rational to mean that it's defined over F. So I actually, that's how I define elliptic curve here. When I said, oh, I didn't say that. A point defined over f, people will say, this will say that is an f rational point. Okay. You can say f point. I'm just saying that the terminology f rational is common. That I think it refers to the fact that the curve is defined over f, and if you could have points that are defined over the algebraic closure of f, or define points that are just at the level of the definition of the curve itself, and that's sort of that's the rational level. So I don't know why, but we do say f rational often. Okay, so can you find a point? Is there a point here that you can tell me? What's that? 1, negative 1, 1. What happens with 1 minus 1, 1? So the suggestion is, how about, 1 minus 1, 1. When x and y, so that would make this vanish, this vanish. Oh, I didn't want to write it. So that would make this vanish, this vanish, this vanish, and this vanish. Everything vanishes. So that point belongs. Okay, so that's an easy point. That's a point? So is that a solution to the original problem? That's 1 apple minus 1 bananas, 1 pineapple. Not good, because there's a negative number of bananas. We have to keep looking. Okay, but we have a point. It's non-singular. It has a point. It's a cubic. This is an elliptic curve. So what can we do with this elliptic curve? I want to find more points. Here are some other examples of elliptic curves. We talked about this one before. This is, in fact, in the projectivization of that one, that becomes Fermat's last theorem for the exponent 3. This is an elliptic curve. This is the elliptic curve that parameterizes squares that are one more than a cube. So that's a natural question to ask. If you're just looking at natural numbers, how many squares are there that is one more than a cube? So the solution is hidden in the solutions of that Diophantine equation, that elliptic curve. This is an elliptic curve. What squares are the product of 3 consecutive numbers? Are there infinitely many such squares? We would have to find points on these to find solutions to those problems. So it turns out, more good news today is that every elliptic curve, so every curve genus 1 that is non-singular and has at least one rational point, there is a change of variables that brings it to a cubic equation, and even better, to a very particular type of cubic equation. So any elliptic curve given by some Diophantine equation like this, as long as if it's an elliptic curve satisfies all the properties, then I can bring it to this format where the AIs are in the field of definition of the original elliptic curve. This is what we call a Weierstrass model for the elliptic curve. This is a Weierstrass model. And moreover, if the characteristic of the field is not 2 or 3, so if you're working over F2 over F3, then you might have to be stuck with an equation like this. But if you're working over Q, over the complex numbers, or over a number field like Q adjoint I, there is actually a change of variables that will bring you to what we call many times a short Weierstrass model. And those are just easier to write down. But as I was mentioning in the session about magma, we do want to consider all elliptic curves. We do want to consider things like this one, or things like x cubed plus y cubed equals 1729, I really want to talk about in how many ways I can write 1729 as a sum of two cubes. So I want solutions to that. So it is important that we can simplify that to certain models that are easier to write down, but we have to be able to go back and forth to all those other models. By the way, note that if you have a Weierstrass model, this is the projectivization of the Weierstrass model. If you have a short Weierstrass model, this is the projective version of the Weierstrass model. And in both projective versions, the point 0, 1, 0 belongs to it. So for example, here, if I put z equals 0, this vanishes, and this vanishes. And if x is 0, this vanishes also, so it belongs. It satisfies the equation. And the same thing happens here with 0 equals 0. All of this goes away. And in fact, all of this goes away. And if x is 0, then that point belongs. So this point is always in these models. So these models have a rational point, which is O, which is the point at infinity. Possibly. Yes, absolutely, because it has to be homogeneous degree 3. So correct. Yes, thank you. Any other questions? All right, very good. So we can bring them to Weierstrass models. Can I bring it to Weierstrass model? Like, let's start first with the sum of two cubes. What numbers are the sum of two cubes? It turns out that you can bring it to this Weierstrass model, y squared plus 9d, y equals x cubed minus 27d squared. There is a change of variables. In fact, the change of variables from one to the other is this map. I'm not going to develop this map, but if you go to the book, I explain how, in particular, how you can get this one with a trick. In chapter 15, actually, I show how to do it for any elliptic curve, how to go from any cubic to a Weierstrass model. What are all the steps that you have to do? So if you do that, or you use Magma, then you can go from this one to this one. And I would like you to try that. So I would like you to, this evening or whenever you want, is to try to do this yourself with Magma. Start with the Fruit-Stefan equation and do all the things that I did before during the Magma session to do all the changes of variables, to find a point eventually that you can bring back to the Fruit's equation that is actually the solution that we want with those giant coefficients. You can do it yourself. So it turns out that this equation is isomorphic to this Weierstrass equation, a nice Weierstrass model. Okay? So now I need points on that Weierstrass model. So again, here's a Weierstrass model. Here's a short Weierstrass model. And it turns out that the Weierstrass models, I could have a Weierstrass model, but it doesn't tell me that that's, just by being a Weierstrass model, it's not automatically non-singular. But the singularities are easy to detect. For example, so there is something called the discriminant of an elliptic curve. For example, for the short Weierstrass model, this is the formula for a discriminant. And the discriminant tells you that the curve will be non-singular if and only if that discriminant is non-zero. So as long as this number is not zero, then this elliptic curve, or this curve, is non-singular, and therefore it is the equation of an elliptic curve. Okay? Hope that is clear that if you have an elliptic curve, there is a Weierstrass model. Not every Weierstrass model is an elliptic curve because Weierstrass models could be singular. But we also know how to detect whether a Weierstrass model is non-singular. Singular? Well, in terms of a Weierstrass model, what are the possibilities for singularities is that I could have, for example, y squared equals x cubed, and that would be a degenerate Weierstrass model because it would have a cusp of that sort. You could also have something like, from the long Weierstrass model, I'm gonna do a cross here. You can have something like this, x cubed minus x squared. The problem with that one is that it self-intersects. It has a self-intersection, and what? Does it matter? Where is the origin? I mean, it is singular regardless, right? Plus x squared. Let me see. I'm not sure. This is x squared times x minus 1. So what's the problem? That's singular, okay? So that's all I'm trying to say. And the problem is at this point, the problem is at this point, that's where singularities are happening, okay? Typically, if it is non-singular,
The origin is isolated. 1 plus some. Then you have an actual. The origin is isolated. Minus. Use 0, 0, the lowest order terms. You can't see the node of the. It looks like y squared is minus x squared here, 0, 0. Y squared is x squared
okay.
plus x squared.
I'm going to trust you in that. Okay, so if the discriminant is non-zero, then you usually have things like they're nice and smooth everywhere. It looks like this, or it looks like, oops, that's not right. You know, it looks like something like this, or it looks like something like this. They might have like two connected components, but it's smooth everywhere. Okay, so the discriminant helps you decide when elliptic curves are singular or non-singular. Similarly, there's another invariant, which if you have a short Weierstrass model, by the way, I didn't write it down because it's a mess, but there's an equation for the discriminant for long Weierstrass equations that does the same job. Yes, Summer?
Does this discriminant have to do with like the discriminant of an n-tuple?
It is the discriminant. This quantity has to do with the discriminant of this polynomial. So if you have a polynomial, you can write the discriminant like the discriminant of a quadratic. You can write a discriminant for any polynomial. So this, I think it's this part, it's related to the discriminant of the cubic in X. Yep. So similarly, if you want to write the discriminant for this equation, what you would do is actually sort of convert it to here and then use this formula. But anyway, you can give it in terms of all the AIs, and it's a little messy. So what I was saying is that you have an elliptic curve, then you have another very handy invariant, which is the J invariant, which is minus 1728 times 4a cubed divided by the discriminant of the elliptic curve. And this quantity actually tells you whether two elliptic curves are isomorphic. If I give you two Weierstrass models, how do you know? Maybe there is a change of variables that goes from one to the other. And it turns out that you can tell whether they are isomorphic over the algebraic closure of F. They will be isomorphic. There will be a change of variables from one to the other, if and only if the J invariants are identical. So that's why it's called invariant, because it's invariant under isomorphism. So the J invariant classifies elliptic curves up to isomorphism. So it's a very handy tool. When I have two elliptic curves and I want to see, like, are these completely different? I can compute the J invariant. If the J invariant are different, then they're not isomorphic over any extension of F. They're not isomorphic over F. They're not isomorphic over any extension of F. Moreover, yes, Colbert.
Can you go back? When you say F bar, is it you mean the algebraic closure?
Yes. Yes, that is the algebraic closure of F. Because sometimes you have elliptic curves that are not isomorphic over F, but they're isomorphic over, say, a quadratic extension of F. So for example, the elliptic curves y squared equals x cubed plus 1 and y squared equals x cubed plus 5 cubed. They're not isomorphic over Q. but they are isomorphic over Q adjoint the square root of 5. Okay, so there's a change of variables defined over the square root of 5 that makes the two isomorphic. And both have j equals 0. It turns out, some fun fact is that there is an elliptic curve with every j invariant. So if you give me any number in your field, f, I can give you back an elliptic curve with j invariant equals that number. If j is 0, then this elliptic curve has j equals 0. If j is 1728, this elliptic curve has j 1728. And if j is not 0 or 1728, this elliptic curve has j invariant j. Okay, so you can actually always come up with one that has that j invariant. So if you want an elliptic curve with j invariant equal to 7, you plug in 7 in there, and that elliptic curve will have j invariant equal to 7. Now, we're interested on elliptic curves over any field. We'll see why, even if you are like very, very much into Diophantine equations, so they're over the integer, so at most maybe you want elliptic curves over Q, but still we will see that even if I'm just interested in elliptic curves over Q, upgrading to the complex numbers tells me something about my elliptic curves. Downgrading to finite fields, so if I reduce the coefficients in my Weierstrass equation, reduce modulo P, and look at the equation modulo P, that information is very important. That's actually how the Birch and Swinnerton-Dyer conjecture came about, was from trying to find a relationship between an elliptic curve over Q and the reductions modulo P. So we are interested in elliptic curves over many fields, and then even over function fields. So you take any field and then do rational functions with coefficients in f. We're also interested in that because, as I said when I was talking about the conjectures about the rank, at some point people proved, first Shafarevich proved that there are elliptic curves with arbitrary ranks over fp. So Shafarevich looked at elliptic curves over fp adjoint t, and found that there are elliptic curves of arbitrarily high rank over that number. No, this is not a number field, over that function field. It turns out that over this type of field, the Mordell-Weil theorem still works. There's still a finite generation.
What's the reference?
What's that?
The reference you mentioned.
Shafarevich. So Shafarevich proved that there are families of elliptic curves over function fields like that of arbitrary high rank. Then Ulmer, the example of Shafarevich, they were sort of iso-trivial. Ulmer found some other sort of or more natural families of elliptic curves where their rank explodes. So because of that, for example, we're also very interested in elliptic curves over function fields.
Could we use the Hasselmann-Minkowski theorem in the reduction of elliptic curves to say something about like the global period?
That is sort of what we do. Yeah, sort of that's the, when we get to Shah, that is what we're going to do. We're not reduction, but embed them into QP. So we look at the elliptic curves over completions and then see what's happening over completions just to see what's happening over Q. The problem with that is that elliptic curves do have points. So of course they're going to have points over every completion, right? But it's these other spaces that we create. That's why we create this sort of other network of Selmer elements where those are the elements that we're going to be checking to see if there's some sort of Hasselmann-Minkowski local to global principle on those elements to try to detect other points of infinite order on the elliptic curve. Over the complex numbers, we are interested because it gives me a lot of information actually over the complex numbers. So if you start with an elliptic curve and then you base extend to the complex numbers, it turns out that there's a theorem called the uniformization theorem that every elliptic curve, or the points on an elliptic curve, are isomorphic to what we call a flat torus. The complex numbers modulo a lattice. And vice versa, if you have a lattice, then this flat torus will be isomorphic to some elliptic curve. So what that means is this picture, that this is what in blue is a lattice, or actually the points in the corners here, those are what would be the lattice points. And when I do the quotient of the complex numbers by that lattice, what it happens is that there's a fundamental domain is sort of like this that is shaded, and this side is identified with this side, and this side is identified with this side, so it becomes sort of some Pac-Man universe. That's a very, very old reference. But in any case, it's sort of like a Pac-Man universe that if you go out this way, you enter this way, if you go out that way, you come in this way in the quotient. So it is a torus, it's a flat torus, there's no curvature. So it's just flat, but it's sort of like pictorially, it looks like a donut. But that it can be used, this isomorphism can be used, for example, to say, like, then what is the torsion on this, this type of, if this is isomorphic, computing torsion here, the structure of the torsion subgroups is not difficult. So for example, what is going to be, if I want to compute, what is the p torsion on this thing? Well, this is sort of like a rank 2 module, and then what you end up computing is that the p torsion, the points of order p, have to be isomorphic to 2 copies of z modulo p. And that's something that is easy to deduce from the structure of, from the complex structure. Okay. So now we want to know more about points on elliptic curves. Yes?
Is this isomorphism going on between the elliptic curves and the lattices? Is that related to, like, I've heard of the J invariant over lattices,
Yes.
but not over elliptic curves. Is that kind of the thing that brings the two together?
It is the same. It is the same object. So the J invariant on lattices is the J invariant on elliptic curves, and that's how we actually, yeah, that's how the two universes are glued together.
So like J of E is just J of lattice, whatever lattice matches up.
Yep, exactly. So if I want to know, if I have a lattice and I want to find out what elliptic curve would match, what I would do is take my J invariant of that lattice, and then since I know that there is an elliptic curve with any given J invariant, then I can find an elliptic curve whose J invariant is exactly that one, and that is going to be the one that is going to match. The actual isomorphism, so this map that actually sends points to points, you have to do some complex analysis using what we call the Weierstrass P function and prove where that isomorphism comes from. But that is, yes, that's a very good point, that the J invariant is sort of like the glue here between the two algebraic and complex universes. So what about points on elliptic curves? Remember, your eye on the prize, we were trying to find a point on the fruits, Diophantine equation. So remember, we had started with an algebraic, with some like genus 1 curve, some elliptic curve. We found a Weierstrass model, and now we want to find rational points on that Weierstrass model. So it turns out that you can do a search here pretty easily for points, and there are points. We already found, well, we found one before, 1 minus 1, 1. There is some other points that are not so clear. Here is one, 8 minus 8. You can bring it back here, and it gives you minus 11, minus 4. So it turns out that minus 11 apples, minus 4 bananas, and 1 pineapple works. For whatever reason, that is not clear at all why that works, but it works. So you can see it here that if you that this is sort of like an equation of 3 rational numbers that is quite surprising to me, but it actually works. So that's a solution. Doesn't work because we want positive numbers. So what do we know about points on elliptic curves? First of all, there is a theorem of Siegel that tells you that if you have an elliptic curve over Q, the integral points actually are always finite. There's only finitely many integral points. So if you were trying to, here for example, just maybe there's a lot of integral points, maybe there are infinitely many, there's only going to be finitely many like 8 minus 8. So I could do some search and try to find all the integral points. In magma, integral points of E tells you all the integral points. But it turns out that Siegel tells you there are finitely many integral points. Baker tells you there is a bound, but look how bad that bound is. Jesus. So it tells you that the max of an integral point, the maximum of a coefficient is e to the 1,000,000 times the maximum of a and b to the 1,000,000th power. It's gigantic. It's completely useless of a bound. But still, the work was groundbreaking, and this was part of the reason why Baker got a Fields Medal. So the fact that there is a bound, an explicit bound, is actually very shocking that one can come up with an explicit bound, even though it's useless. There is one.
Do the integral points form any structure?
The integral points?
Yeah.
No, the integral points don't have a structure. There is, I mean, we can talk later about heights on points and the heights. So you do have a way to get to where would the integral points be. Once we have generators, we are going to be able to figure out how to compute all the integral points using heights, but they don't have, it's not a subgroup, for example. So thankfully, the points on an elliptic curve have a group structure. We did that earlier today. So what we do, this is a generic, a genus 1 curve, so an elliptic curve, without being in Weierstrass form, it has this group structure. What you do is you do the line from P to Q. So you could do this on x cubed plus y cubed equals 1. And you can do addition directly on there. You don't have to go to a Weierstrass model to do it. So you do here, you go here, this point is R, and then you trace the line that goes from R to O, and then this point is going to be P plus Q. Okay, so that is sort of like the generic way of doing it. If you have a Weierstrass model, then it works like this, that you trace the line here, then you reflect, and this is going to be P plus Q. Okay, and it works the same way because what did I do here? I did, once I found the third point of intersection, I drew the line from R to O. What is this line? This line, if I draw a vertical line, remember that every vertical line actually goes through O. So it is the line from O to this point, it is vertical, and then I find the third point of intersection. That's how you find P plus Q. And so again, as an exercise, if you've done some projective geometry, then try to prove that if you have in the projective line, and in the projective plane, every vertical line goes through 0, 1, 0. So you have to put everything in projective coordinates, and then you just check that it's true. Okay, so now I think I started a little bit late, so I'm going to go until 5, so I have a few minutes. On this elliptic curve, I just wanted to show you that this point, if I drew this more or less correctly, that this point has actually finite order. So this point, if I try to find 2p, what I would do is draw the line that goes from p to p, so the tangent line at p. The tangent line at p goes like this, and this is the third point of intersection of that line. Then reflect it, and this would be 2p. Then I add 2p and p to find 3p, and I draw the line like that. It goes through here, and then reflect it, but because it's in the x-axis, that is 3p. To find 4p, I'm going to add 3p and p. So 3p and p, the third point of intersection, is here, reflect it, and then this is 4p. By the way, I could have done 2p plus 2p, and you get the same thing. And then 4p plus p, I have to do the line from 4P to P. It's already drawn. Whoa, what just happened? It's a 479% zoom. The heck? Okay, so the line from 4P to P is drawn. The third point of intersection, because this was a double point, is here again, and then reflected, and here is 5P. But now 5P and P are in a vertical line, so when I add 5P and P, the third point of intersection will be whatever the vertical line touches, but they go through the point at infinity. So it will go through O, and therefore 6P is O. So 6P is 0. So P is a point of order 6. So it's a torsion point. You can do that over you can do this manually, so you don't have to just do it by drawings. In this elliptic curve, you can add this point and that point. Those are points on this elliptic curve. And to add them together, first you come up with the line that goes through P and Q. So this line here is the line that goes through P and Q, and intersect it with the equation of the elliptic curve, and that will give me cubic. But now this cubic, I already know that 5 and minus 4 have to be roots, so I can factor this cubic. Factoring a cubic is not quite easy, but if I know 2 roots, then for sure I'm going to know the third root. And this is a root that corresponds to the x-coordinate of the third point of intersection with the line, and therefore the addition will be this point. Okay? You can also do the same thing, but with 2Q. You can double up, and now this line right here, what is it? This is the tangent at Q, which you can find using, for example, implicit differentiation to find the slope, and then use the slope and point formula for a line. You can also do addition over a finite field. Just the same formula, so now you can also do sort of like the lines, but now there are formulas to do addition, and then you can do it all modulo 11 and do addition over there. So for example, in this elliptic curve over F11, you can compute the discriminant. The discriminant, what is that? I forget, but this discriminant is non-zero modulo 11, so it is an elliptic curve. This is a point on the elliptic curve, and then you can find multiples of that point modulo 11, and you can just figure out what the multiples are until 12P. So it turns out that P is a point of order 12, and in fact, that point generates all the points on the curve over F11. These are all the points, the points I just drew. These are all the F11 rational points. So every point, so it turns out that is generated by the 0.75, and it is isomorphic to Z modulo 12. Okay, back to the Weierstrass model. This is the Weierstrass model for the fruits equation. Remember we had P 8 minus 8? That didn't work because that gave me the solution, what was it, minus 11 minus 4, 1. That's not good. But now I know that I can do addition. So what if I take this point and double it up and see what happens? So if I double the point, I get this point, and I can send it to the fruits model, and it tells me that minus 8,784 apples, 5,165 bananas, and 9,499 pineapples also works. It still doesn't work because of this. So that doesn't work. There are more points. For example, I can actually, if I do a search, I find another point, 23 minus 103, and it doesn't work either. That actually gives me this point, which is equivalent to the one you mentioned. Twice this point gives me another point, which is also not good. But we're closer now because it's like 1 apple, 0 bananas, and 1 pineapple actually works. But it doesn't work because I have 0 bananas. So what else can I do? Well, we're going to be talking about a little bit more. I'm going to need some more about theorems about f-rational points. But I think I'm going to stop here so you can keep you on your toes. And in my 3rd lecture, we will find a solution to the fruits problem. Or in the meantime, hopefully, you can find your own solution now with what we know. So I'll stop here, and we'll continue tomorrow.